Thank you very much for having me. And so this talk is about shared state in PureFP when a state model won't do. So the first objective of the talk is to explain what all these words mean. And then I'm going to try and argue about why you should do your state in a purely functional manner. Why does it matter? But also, how is it done practically? So hopefully you get some practical advice, because I feel like this is a key step from being someone that can understand the libraries a little bit to someone that can write a whole system purely functionally. And I got this question on GitHub like loads of time. So I thought I should just probably do a talk on it. My name is Fabio. I am a software engineer for Over Energy in London and an open source contributor at System of Omega. I am a core contributor and maintainer of FS2, and a maintainer for Cat Effect, HTTP4S, CATSMTL, and a bunch of other stuff in the PureFP ecosystem. So I've already said PureFP, so the first thing is, what is purely functional programming? Because I feel like for loads of people still, PureFP is that thing where you don't write to disk, which is nonsensical. How do we write stuff, right? Where in fact, it's something different. So purely functional programming has a lot of concepts and techniques, but actually it all boils down to a very simple property, which is called referential transparency. And referential transparency says that you can always replace an expression for its bound value without changing the result. And although this seems complicated, it's something that most of you are already familiar with from school. If I tell you x plus 2, and then I tell you that x is 1, what do? You replace x with 1 every time you see x, and then reduce. And what this property says is that simply you should be able to do the same with your code. So let's have a look and see if we can do that, and when we can do it and when we can't do it. So I've got this very simple example. I've got a string, hello, which I'm reversing, and then I am appending this string to itself. And the result is hole hole. And then I want to apply the referential transparency transformation. So I'm just going to replace x with its value, just like you would with a number. And you get hello the reverse plus hello the reverse, which is hole hole again. So doing the transformation did not change the behavior. So this is pure. It's referentially transparent. But now what about this? So I've got this integer that comes from started in, and then I sum it to itself. So I read from started in once, and I get a 2, say, and the result is 4. What if I apply the transformation now? Well, if I do it, now what's happening is that I'm reading from standard in twice. So doing the transformation changed the behavior. So this code is not referentially transparent. This code is not pure. What about future? So future is actually exactly the same, because future would just start the computation immediately, and then the result will be shared the next time you reference that future. So if I do read, the first one will call standard in, and the second one will just access the result. So it's kind of doing this sharing or memoization or whatever you want to call it of the result. And so if I do the transformation, again, the behavior changes. So this is not pure. And by now, many people think, okay, then reading from standard int is not pure. But that's not the case. It's just about the property. Can we make it respect the property or not? And as it turns out, yeah, we can. We can use this type called IO. This is from Cat Effect. And IO does not start the computation. It just describes the intention to do it. And then you're going to run it at the end of the world. And so when you do read, is you're basically saying, I want to have the program that reads twice. So what's going to happen when you run it, in your main or whatever, is that it's going to read twice. And if you do the transformation, the same thing happens. It's going to read twice. So doing that substitution did not change the behavior. And by definition, this is pure, because this is the definition of pure. And so you can look at this read as like a command that, or a recipe or whatever. But at the end of the day, this is the transformation that matters. And also, I've had a lot of people tell me, okay, but how do you read once? It's fairly easy. You just read map x to x plus x. So you call the command once, and it's going to read once. So IO is pure. There's no tricks, because that's the definition of purity, and IO respects it. So what's PureFP? So side effects are things that break referential transparency. That's it. So IO, state, and so on are traditionally side effects, but they don't have to be. You can, if you do them in a way that's referentially transparent, that they're not set effects by definition. And so this sort of explains the what, but then why. Okay, I've got this property, cool. Why do I care? And obviously this is a whole other talk, so I'm just going to touch on it. But the key idea is that referential transparency sort of begets local reasoning, which begets awesomeness. Because if you think about it, the fact that I can always replace an expression for its value means that that expression does not depend on a context. For the very broad sense of context, it might be what happened before, or where it is, or, you know. And that means that I can always reason about things locally, with local reasoning. I never have to have two things in the same time in my head. And that's awesome. So one example I want to make is sort of compositionality. So the ability to understand code by understanding individual parts and then putting them back together. But putting them back together is exactly doing that substitution when you replace a thing for its value. And if you're not guaranteed that that substitution won't change anything, then you can't do that split. You need to reason about this in a global fashion, both things at the same time. And that eventually leads to that feeling of having too many things in your head at once, and then someone sends you an email and it's gone. So this doesn't happen. And that's amazing. And there's also, there's a bunch of other things which I don't have time to touch on. And also, referential transparency is also known as purity. So purity doesn't mean I'm not reading from disk, because otherwise I couldn't write pure code. It doesn't make any sense. Purity means that all of my code is made of referentially transparent expressions. So it's a syntactical thing. It's not a moral quality. So just to get that out the door. So referential transparency is awesome in general, but today I want to talk about a very specific thing, which happens when it interacts with shared state. I think obviously it all sort of derives from the same thing, but it's good to highlight as a specific property. And as I said, I want to show you both why and how. So first of all, let's talk about state. And so the first thing is that local state is off topic for this talk. So what do I mean by local state is something like this, where I got a map on a vector, just vector f, a, and b, and I get a vector b. And for whatever reason, performance or whatever, I want to do it with a var and a mutable buffer and what have you. But from the outside, that function is still perfectly referentially transparent, even though the body is not. And so this is kind of local, and I don't care. But do note that having state encapsulated in an actor or an object is not the same thing as this. It's encapsulated, but it's not local because the interface that interacts with it is not referentially transparent. So this only applies for this sort of thing, which is like pure transformations, which are implemented in this way, normally for performance. There really isn't any other reason for that. So I don't care about local state, because from the outside, this function is referentially transparent. I care about shared state. And the first thing we're going to do is have a brief look at the state data type, the state monad, and then look at the limitations of state. Why we can't use it, why a state monad won't do in many cases. So what is state? Is a data type with two type parameters. S is the type of the state, say an int, and A is the result, whatever, unit, string, what have you. And the way you can look at this is that state S of an A is a computation that describes modifications to an S, which result in an A. So he says, if you give me an S, I can apply a series of modifications to it, which then result in an A. And S can be any immutable data type. So state basically describes how you take an immutable data type and have very varied copies of it until you get to a result. And I'm going to show you how actually it works. It's actually pretty simple. And so since you like applying all these modifications to a given initial state, the way you run a state computation is simply by providing an initial value. And the way you build state programs is by using its many algebras. So the monad, that's why it's sometimes called state monad, applicative, and what have you. So I'm not going to mention state T or index state. For those of you who know who they are the same with respect to this behavior that I'm going to talk about. So how does it look? For now, just focus on the first line, so the definition. So state is something that wraps this function that takes an S, so your state, and returns an A and another S, which is a modified copy of it. So yeah, you basically describe stateful things as I take an initial state, and then I'm going to return a modified copy of it. And that's the next state, and return an output. And so a state computation is uniquely defined by the shape of that function. And when you assemble state computations together, what you're doing is basically building this complicated function. And once you're done doing that, you want to run it. Since it's described uniquely by this function, all you need to do is to provide an input for the function, which is the initial state. So to run a state computation, you just pass the initial state, and the function will apply the modifications and give you the result by taking the first element of that tuple there. And how do you compose this state together? You don't want to obviously run and rewrap and then run and rewrap. You want to compose them in the state context and then run it sort of when you're done. So you can use flat map. And what it's saying is that if I have a computation that will apply some modifications to S and then result in an A, and then a function that, given the result of that, given the A, returns another state, I want to sequence them together by passing the state through this sequence. And it's very easy. You just call the constructor. You need to pass a function. So given the initial state, what modifications should we apply? Well, we can call modify, our own modify, on this, and this will give you the result and the next state. And then I can use the result to call f, because that's an A, and now I have the next computation, and then I just pass the next state to the next computation. So what's happening here is basically you're threading the state through a series of computations. So that's all the state monad does. And then in the companion object, you have these three sort of primitive combinators. So pure takes an A. It's just a way of saying I want to have a state computation that returns a result without doing anything to the state. And if you look at the definition, it's exactly what it's doing. It takes the state, the input state, and just returns it unchanged. See? Takes the S and returns the same S. So it's not doing anything to the state. And the output is going to be the A that you pass in. And for those of you who know, pure and flat map are what makes are the combinators that make something a monad. So that's why the state monad. And then I've got these two primitive programs, get and set. And so get is something that will return the current state without touching it, without modifying it. And again, you can see it. It takes the initial state, and then it just returns it as the second element of that tuple without doing anything to it. So it's not doing any modifications. And the output of this computation is S itself. So I'm getting the current state. And set is kind of the opposite. So it takes the next state, and see the function just ignores the previous one because we're discarding it, right? We're setting a new one. And then the output is unit, because there's no result of when you set something. And the new state is the state that you set. So, I mean, you don't have to necessarily understand kind of all of it, but just know that it kind of fits in one slide. The cats one is a bit more complicated, but there's not much more to it. So let's now look at an example of how you could use this. And a sort of typical example is a kind of game run loop. Game as in, like a video game or something. So this still trait command, imagine like the sort of things you can do to a character. And it's very easy. I can sort of damage their health or heal them. And they both have an int, which is like the amount by which you want to sort of affect them. And then the first thing I want to do is have this little helper combinator update that takes a function from S to S, so something that can change the state, and returns a state of S unit. And I can use it for comprehension because I have flat map, the state is a monad. And it kind of reads nicely. I'm just going to get the state, the current state. I'm going to modify it with that F, which returns a new state. And then I'm going to set the new state. So that's it. And then health is this, it will take a command and sort of do the appropriate thing. So I'm just going to match on it. And in case of damage, I'm going to return a state program that updates the current state with mine by detracting some health. And if I want to heal them, I'm going to do the same thing, except I'm going to increase their health. And then I've got this separate program, sort of report, which just gets the current state. Sorry, sort of scores. Oh, shit. Sorry. So it gets the current state, and then just sort of maps on it to change it into a string. And then I've got this sort of list of commands, sort of damage, and then heal. And this is all nice. It's like a lot of algebraic combinators. I can now build a bigger program by combining those ingredients in a way. So I'm gonna, there's no one well done. I'm just going to traverse commands. So traverse sort of traverses a list with an applicative play with the context. So you can think of it about it as some sort of purely functional for each in sort of layman terms. And for each command, it will just call elf and then report. And once I'm done sort of building this, I'm just going to run it with their initial state. And the result is that the current health is 9 when I damaged 1 and started by 10. And then it's 4, and then it's 6, because I've done some healing. So actually, this is kind of awesome. So first of all, it's pure. I haven't done that substitution, but you can do it for yourself, and you can see that it does respect the property. It's very compositional. I've got all these little nice programs, which are independent, all make sense on their own, and I assembled them to build more complicated behavior, which is really nice. And it's also testable. So very often, you want to test something by starting from a given state precondition. Okay, what happens if I start with this state and then do these actions? And it's very easy. We say, just provide a different initial state. What if I start with 0 and then damage? What happens then? So it's quite nice and testable. So this is all great. But so what are the issues? Why a state monad won't do in many cases if it's that nice? So the main issue is that threading an S via this function is an inherently sequential thing. You are literally passing something from a function to another, which is sort of the most sequential thing you can think of. But in sort of the typical server-side applications that I write, and I assume many of you also write, most state is concurrent. Think about a request counter that counts how many requests you're getting. Obviously, all the requests are getting there in parallel. Or a cache. You've got readers and writers. Again, this is concurrent. Or a queue with producers and consumers. Again, this is concurrent. Or a rate limiter with multiple requests. Or a finite state machines with different messages, kind of like an actor-like thing. And this is all concurrent state. And state cannot do any of that because it's sort of tied to this sequential chain of things. Also, sometimes what you have is already mutable. Let's say you're dealing with a JDBC connection that gets there from JDBC. This is already mutable. How do you make sure that, how do you work with it in a referentially transparent manner? State has nothing to say about suspending mutability. It just says, you give me an immutable thing, and I can describe updates to it. So state just won't do in many server-side cases, and just in many cases in general, even though it is nice, and it does have its use cases. But so what should we do? State won't do. Can we still keep the nice things about it, like the compositionality and the referential transparency, while supporting all these scenarios? Well, as it turns out, we already seen something that can make anything referentially transparent, right? This is I/O, because of this suspension of effects. So for those of you who are not super familiar with it, I/O is a computation that will produce one value, fail, or never terminate. This is like its behavior. It's referentially transparent, it's pure, and I've shown you with an example at first that this is the case. I'm not hand-waving it. It's not signaling effects, it's pure, there's no catch. And can suspend any side effect because of, it doesn't evaluate eagerly. It evaluates at the end where you can't observe the side effects anymore. And it also has many algebras. So monad is the famous one, the I/O monad, but cat effect adds several ones. The sync, which is the algebra of things that can suspend side effects, and then concurrent for like fibers and things like that. No, we're not going to touch on these too much because, again, that's another talk. But just know that it's got several algebras to work with it. And something like Monix task fails in it's the same category. Something like scala-italy is in the same category. Something like future is not in the same category because it cannot suspend side effects. And that's kind of like the key thing here to keep referential transparency. So the main idea is that concurrent shared state happens in I/O. You need the power of I/O. Or any F with a suitable type clause. So a list sync. So it means you can use I/O or task or whatever, but not future. And so how should you approach the design of this sort of shared state aspects of your code? So there are basically two things you can do. You can either wrap mutable data directly with I/O, or you can use cat effect primitives with immutable data. And what you should do is use primitives whenever you can, which is actually most of the time. And then when you actually must do it, just directly wrap. And I kind of wanted to show you both things. I wanted to show you both things. So I thought of doing it this way. I'm going to show you how a primitive is implemented, and that's an example of direct wrapping. And then we're going to use the primitive, and that's the example of using the primitives. And the recipe for wrapping is actually very simple. Access, modification, and creation of mutable state needs suspension in I/O. And normally people see why access and modification have to be suspended. They don't really see why creation also needs to be suspended. But if you don't suspend it, then you're going to get the same sharing you have with future, which will break the property. But this is like a sort of a dumb recipe. You just do that, and it will work. Just don't forget to do any of these pieces. So I want to introduce now the primitive that we're going to first implement and then use, which is a ref of f and a. So the f there is the so-called effect type. So just imagine it's I/O or task. And a is the content of this ref. And what ref is a purely functional, concurrent, lock-free, mutable reference. So it's purely functional because it's referentially transparent. It's concurrent because concurrent updates are sort of thread safe or fiber safe or whatever you want to describe it with. It's lock-free because it doesn't use a lock. It uses sort of non-blocking Java primitives, which means it never blocks a thread. It's at much higher throughput than locking or synchronized. And it's a mutable reference because it adds this sort of purely functional mutability aspect to any given A, any given immutable A. And this is the interface. So it's a trait, and the F again is the effect type, I/O, and A is the content. And you can get, which returns an F of an A. You can set, takes an A, an F of unit. And then the interesting ones are update and modify. So look at update. So why do I need update there, and I can't just do get and set? Because remember, this is concurrent. If you get, and then someone else sets, and then you set, that's a race condition. So you need an update function that does it for you. And again, this doesn't use a lock. We'll see how it's done to make it work without a lock. And then modify, I'm not going to talk about modify in this talk. Basically allows you to thread an action alongside your modification. And this is super useful to implement finite state machines, kind of like a purely functional actor. I use this pattern a lot. It's really awesome, but I don't have time to go into it. And then the other important thing, if you look at create, it's parameterized by the F, again, the effect type, and it says that it has to be async. It has to be at least as powerful as wrapping side effects and suspending side effects. It can't be future, it can't be option, because otherwise you're going to lose the referential transparency, which is the point of this. And then it has an initial value, and then returns an F or ref of F of A. And this shape might be unfamiliar, but you need to familiarize yourself with this because this is super common. F of thing of F and A. You're going to see it all over the place because the F is the action that will create it. If you just see F of A, it means that either it's not pure or it's not actually mutable or effectful. So if you see that in your code, it means that you forgot to do that aspect. So don't do it. And to implement it, I'm going to just do a slightly simplified version where the effect type is just hard-coded to I/O. So I'm going to do an IRF. Is the same, just like to keep it a bit simpler. And I've got this class. Again, just look at the first line for now. It's a final class because I don't want people messing up with it. And it's got a private constructor and a private thing because I don't want other people accessing the mutable state because that needs careful suspension. And the state is an atomic reference. So how many of you have ever seen an atomic reference before? Yeah, some people, not a lot. So atomic reference is not a functional thing. It's a thing that comes with a JVM that gives you non-blocking concurrency. And it's an intrinsic operation that the JVM provides you. So it's not a lock. That's the key thing. And to implement it, you just wrap operations on that thing. So get, atomic reference as a get method. You just suspend it in I/O. Same thing with set. And update is like the slightly more interesting one. And this is like the non-blocking aspect. It's not important to understand how it works for the purposes of this talk, but I'm going to try anyway because I think it's cool. So it's got this loop, which is a tail recursive function, which calls, and again, the whole thing is suspended in I/O, again, for purity. It's going to get the state from the atomic reference. This is then your copy of the thing. And then returns a modified copy of it with the F, your update function. And then it's going to say, if I know that the old state hasn't changed, so if I try and, that thing is called a compare and set is like a CAS loop, compare swap loop. It's going to say, if the old state is equal to the state I had when I read, it means that it hasn't changed. It means that no one else has concurrently updated it. So I can just update with my one. And if it hasn't, then I need to retry. Something else has happened. And note that that compare set does not block a thread. It's like atomic operation that the JVM gives you. So this actually has a much, much higher throughput than logs. You might think it's not the case because of all this busy retry, but actually it's so much faster, and it also guarantees progress. If this can never succeed, the thread is not blocked. Other things can go on. So this is pretty awesome. It's pretty awesome, but from a functional point of view, I'm not doing much. I'm just putting the whole thing in I/O. It's not complicated. It doesn't need an expert in functional programming. And to create it, it's the same thing. I'm just going to create a new IRF with a new atomic reference with the initial value, but be careful about wrapping it in I/O. So even if you didn't understand any of this, it doesn't matter. There's a very dumb thing to do. Wrap every operation in I/O, wrap the constructor in I/O, and make it private. Make sure that people cannot go into the sort of tricky and finicky bits of it. So that's it. And this applies to your code as well. If you're dealing with a JDBC connection, you're going to wrap every operation on that connection with I/O and creation in I/O as well. And that's it. And so, again, this is like how you do it polymorphically. It's the same code, just sort of moving things around a bit. So it's a trait. And then create, I just take the sync, and I call sync delay, which is the equivalent of suspending for an arbitrary sync, with the new atomic reference. And when I map on the I/O, I get the atomic reference, and then I wrap all the operations. So same thing. I just moved code around and made it a bit more polymorphic. So that's how you wrap, and that's how the Cats effect internals work. It's a cool type. I created it for FS2 first, and it's in Cats effect now. But how about using this, which is kind of sorry, more relevant to what you do sort of most of the time. So first of all, a little trivia. I got this program, counter. I can't create the counter, which returns an I/O of ref, I/O of int, again, the same shape. And then it's for comprehension. I get counter. I need flat map to get into the ref, and then update with +1. And then counter, again, flat map to get into the ref, and then .get, and then I yield the result. Does this make sense to people? And I get some nods if it makes some sense to you. You've seen them. So how many people think that when I run this, it will return 1? Don't lie, because I'm going to ask you why you think so. Yeah, it seems reasonable, right? You're just doing getting and then updates. Why shouldn't it return 1? But actually, this returns 0. And the reason you might think that it returns 1 is because you're used to set effects, where calling counter twice will access the same thing. But as it turns out, there's a very, very easy way to understand what this does without having to think or without having to be skilled enough functional programming. And it's the same dumb substitution that I showed you at first, where you just replace things. So let's just try replacing the definition of counter into counter, which we can always do because this is pure code, by definition. Oh, look what's happened. The first line, ref create, and then I update the ref, and then I just discard the whole thing. And then I create another ref, and then I get on that one, and that one has never changed because it's a different thing, and so this thing returns 0. And at this point, people go crazy on GitHub. It's like, okay, how do I make this work? The typical question is, how can I memorize an I/O? But what they're actually asking is, how do I make I/O side effectful? Which is like, that's not the point. And the funny thing is that the solution is super easy. I've never seen, typically people understand it immediately, but also they never quite get it on their own. It's like this sort of impossible thing. And let's look at it. It's nothing magic. So the counter is the same, but now the prog just takes a ref as an input. Not an I/O of ref, just a ref. And then I just call update and get, and I know it's the same ref. And in main, I just create the counter and flat map it into program. And when I run this, this will return 1. And again, if you're not convinced, there's a very easy way to understand it. I'm just going to replace counter with the definition of counter and prog with the definition of prog, which I can always do. And there you have it. I'm going to create the ref, initialize to 0, flat map, yeah, the counter, and then you first update it, and then you get the result, and that's it. So obviously, this is a sort of single fiber scenario. There is a way of making it work for concurrency. I didn't want to explain class-effect concurrency as well, but it's not relevant. The relevant bit is the creation of the thing and the substitution that helps you understand how things work. But now you might think that the first example was broken and the second example wasn't. But actually, they are both very useful because the second was showing us how to share some state, but the first was showing us how to isolate some state. And in real code, both of these things are really important. So I've got another small example for this. So imagine I've got this purely functional cache implemented on top of ref. Again, IO cache, IO user with cache create. And then two programs that use the cache. So in one scenario, one feature, I want these two things to have separate caches. Maybe they have different strategies for upgrading them. I don't want them to mix. And I want to have a guarantee that they will never mix. And that's very simple. I just flat map on each program. But then for another feature, I actually want them to share the thing. Maybe one is producing and one is consuming, and so they have to share it. And again, this is really simple. I just create cache sort of above, and then flat map the same thing to both programs. And so I hope you would agree that both of these things are valuable. And having these guarantees for both is valuable. So how does this work? Basically, you create a region of sharing just by passing arguments. By passing the cache, you're kind of defining this region of state sharing. And then you just seal the region once you flat map. Once you flat map, it's kind of, you say, like, you define the boundary in which they're sharing the same thing. And the higher in the call graph, the more you're sharing. Just look at the first code. You've got cache and cache, and they are not sharing anything. And then you're going to just hoist the call to create upwards, and now they're sharing. And if you keep going up, you get to main, and now you've got the equivalent of a global thing that all of your program is sharing. And this kind of leads us to the key, the slide of the talk, so the most important one, which is the key property of shared state in purely functional programming. The region of state sharing are the same as your call graph because of all these things that are created, all these regions are created by passing things around. So we've transformed some dynamic behavior, which is who shares this state, into a straightforward syntactical property, who takes this argument. We also can always understand any part of this code just by substitution, as I've shown you. No matter how complicated it is, I can always substitute and see what happens. Also, I have no spaghetti because I have controlled sharing and isolation. So spaghetti is exactly code where you can't quite tell who's accessing who, and you can't sort of pick it apart. And you can control that. And also, it's kind of testable by default, because to make things shareable, you have to inject them. And so now you can pass, a test state or whatever. And with all of sort of very simple technique, just passing arguments and flat mapping. There's nothing magic. And so for the final bit, I just want to talk a bit about sort of final tagless. And final tagless is a term that means, you represent an algebra in terms of its eliminators. But what it is practically is just a parameterized trait with functions. And we've already seen one, so no worries. So this is a final tagless algebra. So it's a trait with a type parameter. And you have instances of the trait, and it creates things. But the point I'm trying to make, in the code I've shown you so far, different bits and pieces were all accessing the state and doing things on it. Whereas it's better to build an abstraction that describes what you want to do semantically in terms of your domain, and encapsulate the actual state manipulation in the interpreter, so to speak. So for example, the counter thing, why do I don't want this to be a ref that I increment. I want it to be a counter abstraction. So just a trait counter takes an f, and I can increment, get, and reset. And then to create a counter, I'm just going to call ref create, and then I access it, and then I implement the things by calling the appropriate methods. And note how there's no explicit suspension anymore. We're now in a land where everything is in terms of cat effect primitives. You don't have to worry about messing up. It's all pure, and it's all sort of nice. And as an example of use, I have this stick function, takes a timer. This is a cat effect thing for like waiting and sleeping. And this counter, and it's going to sleep for 1 second, increment the counter, and then sort of do it again. which is a sort of simple use case. And this one, in turn, can be abstracted. So you can have a trait ticks that returns a stream of ticks, and the constructor is going to call this function, and so on. And so you kind of build this nice domain where everything is easy because it's the language you picked, and then you implement the sort of the primitives. And so as it turns out, this pattern is really common because it's really useful. So I've got some examples from stuff kind of work on. So in cats-effect, you have ref, deferred, semaphore, and var. All the same, these traits with the shape of the constructor being f thing of f and a. In FS2, there's q, signal, and topic. In HTTP, this is a client, and people are confused by this. Why is f client of f? Because actually there's some state being shared there, and that's a connection pool. And so with the same technique, you can decide which calls share the same pool and which calls don't, with the same nice, very, very simple mechanism. And then I got this final state machine to sort of represent reactive stream subscriber, limiter. And this is not something I work on, but it's very common. Adobe transactor has the same shape. F transactor, F of A. And build your own business abstraction. And actually start from the abstraction, build a language where everything is easy, and write code in terms of that language, and then just implement it using these primitives. And I do this for most of my code. It works really well. And then I just want to touch that you can actually have more than F in some cases. It doesn't have to be I/O. For example, you can have resource FA. This is another cats-effect thing that adds a resource safety for things that have to be shut down. So an atomic reference doesn't have to be shut down, but a connection pool might. Or it could be stream of FA, which has resource safety and streaming and concurrency and control flow. But like I've got other talks on stream, you can check that. So as a recap, so first of all, referential transparency rules. This is not a moral property. It's not a mathematic, it actually helps you in real code tremendously. It's a game changer. And the second is that concurrent state needs to be in I/O. State is cool, but it's sequential, and what we care about very often is concurrent. And then to share state and to not share state, just create these regions by passing arguments. It's all about passing arguments. It's super simple. And then build your abstraction with tagless final or your favorite technique. I've just picked this one because it's particularly nice and it works well in Scala. So in conclusion, concurrent shared state and effects in general are not a weakness of PureFP. They're a strength because of all this property. I do PureFP because I want effectful code. If all I had to do was pure algorithms, I could do it with while. It's fine. But when the hard stuff comes, concurrency and mutable state, then I want FP. And that's all I have. So if you've got any questions, just ask now or later. And I'm also on Gitter or a system of Omega. Just feel free to text me or chat to me. And if you didn't understand anything or something, I will go ahead and try and explain again. Thank you very much. See you, Chris.
So questions?
If you see your Twitter handle, from the system Omega in
What do you think? Yes.
That's very personal stuff.
Yeah.
You shouldn't have such intimate questions.
Anyway, yeah, so again, it takes a while to get used to this. You need to write code. So just getting it shown to you doesn't necessarily sort of, oh yeah, I get it. The slides are going to be on my GitHub very soon, just straight away. And then feel free to pick me up or text me later. And yeah, thank you very much for having me again.
Thank you so much, Fabio.